Okay, so in this video we'll look on how we can use the Clark oxygen electrode to measure oxygen appearing or disappearing. It's composed of 4 units. One of the main units is the cell assembly, which is over here. In here you actually have 4 cells that are immersed in a water bath. The water comes from this bath. It is at 37 degrees and it's being circulated around these cells, so this way we keep the contents of the cell perfectly at 37. And within the cell we have a large brown magnet, okay, that will be turned on when the time is right to keep the system homogeneous. Over here we have the electrode itself to measure the oxygen, and this unit is the amplifier. So eventually the electrode picks up a micro signal, sends it to the amplifier, gets amplified, and then the data will get shipped to the recorder over here. So on this recorder we'll pick up the signal. Okay, let's have a look at the Clark oxygen electrode. It's made of 2 metals, silver and platinum. Over here we have the electrode body. We have the electrolyte to form the salt bridge, the membrane, the O-ring applicator, and the O-ring itself. We have a large piece of silver on the outside. We have a brown polymer that is inert, and in the center of the polymer we have the platinum wire. So now we will adapt a membrane to the electrode, add 1 drop of KCl to form the bridge in between the silver and the platinum. Then we stretch the membrane across, capture part of the electrolyte, and then we slip on the O-ring. At this point we have a functional electrode. We need to get rid of the excess membrane. Now we'll adapt the electrode to the body. So we slip the electrode in. We turn until the tip is resting. One thing to notice on the body of the electrode is we have an opening, like a slot, from the tip to the top, and it is via this opening that we'll access whatever we have in our incubation mixture. And we also have a depression here. It's called the overflow groove. Okay, so now we're going to look at how we make a measurement with a Clark oxygen electrode. In the cell assembly we're using 2 cells. We have 1 cell with 3 mils of buffer, and right beside it in the other cells we have our yeast suspension, which we'll be using to cause the disappearance of oxygen. And what we have to do now is introduce the probe into the cell. So we need to rinse the probe, and then we take off the excess water using a Kleenex, but we must not touch the membrane. So you wipe the outside of the electrode, but you don't touch the membrane. Now when you put the probe in, one thing to notice is at the top we have these finger-like devices that to put friction on the body of the electrode. So you rest the electrode on these fingers and then you press it in. And the other thing that's important, you need to make sure that you keep this groove here towards you, and then you press it down using a twisting motion. When you're close to the solution you stop the stirring and then you evacuate the air from the chamber. And the easy way is to lift the cell assembly and just go down slowly using the twisting motion. The air gets compressed and evacuated through the opening. And the objective is to have a minimum quantity of liquid in that groove and down, and we start the stirring. So at this point we're ready to do calibration. So now we're ready to do calibration. One thing before we finalize the calibration, we need to understand what's happening within the cell. We have to remember when we prepared the electrode, we added an electrolyte to join the platinum to the silver, and we put a membrane. This membrane is permeable to all gases, but within the membrane only oxygen is disappearing. So when the system is plugged in within about half a second, we are very low in oxygen within the electrolyte. So it means the oxygen that's in our buffer will start to diffuse across the membrane to reestablish the O2 concentration in the electrolyte. And within a few seconds we have a gradient established, and when we have this gradient of diffusion established, we have a constant signal that is proportional or equal to the oxygen in the buffer. Now this is a micro signal, and it travels down this lead, will come to this amplifier, will be amplified by a number of units, and then the signal will be shifted or sent to the recorder. So anything happening with the oxygen concentration will be recorded on our linear recorder. Now what we have to do now is, using this knob, we need to amplify the signal, and usually we use the 100%. We use 100% as our target. It's about to get there. You can see the pin is moving up, so the movement is proportional to the amplification. And when we reach 100, that's good. We'll turn on the recorder. So at this point we're ready to add the yeast to the cell. Okay, so now we're ready to put the yeast into the incubation. We'll be doing this by using a capillary, this capillary over here. And then what we have to do is load the capillary with the yeast, and then find the opening that is here, slip the capillary down into the chamber and add the yeast. Before we use the capillary, we need to wash it, so we'll rinse it once with water. 2 or 3 times is usually recommended. So now we're ready to pick up the yeast. First thing to do is compress the piston, evacuate the air, and then put the capillary in the yeast suspension. And once it's in there, it could bounce around because of the magnet. That's okay. The key point is release the piston slowly. Take up your sample very slowly, because the yeast suspension has a higher viscosity. And when the piston is released, this part here is released, wait a few seconds for pressures to equilibrate within the capillary, and withdraw, making sure you have no air bubbles at the tip. And then you can use one backstroke motion to clean the droplet on the outside. Take the capillary, guide it into the slot, push it in until about halfway into the chamber. Then you add the yeast. You add slowly. You do not use the second stage. When you reach the first stage, you keep it compressed, withdraw the capillary, expel the last quantity, and right away rinse. So when you're adding the yeast to the chamber, if you use the second stage, you'll be injecting air into the system. And it's imperative that we only have the oxygen or the air that's dissolved in the buffer. Now the yeast has been added to our chamber. It is kept homogeneous by the magnet. Now initially we calibrated the signal coming from the buffer at 100%. Now the yeast is in there consuming the oxygen from the buffer. Therefore we're reducing the amount of oxygen available to equilibrate with the platinum, so we have a decrease in concentration, and this will be amplified by the unit and then recorded. Okay, so now the yeast has been added. So what's going to happen is the yeast will consume the oxygen that's in your buffer, and this will reduce the amount of oxygen available to support the gradient that we call our 100% signal. Now if we glance at the amplifier, we'll see we've gone from 100% to about 60%, indicating that 40% of the oxygen has been consumed. And on the tracing on the recorder over here, we've been tracing this for a couple of minutes now. We're observing a slope. We have a graph that is time on the x-axis versus oxygen on y. So we have a slope that is the disappearance of oxygen with time. Okay, so now we're ready to clean the cell. So the probe comes out back into the beaker to minimize drying of the membrane, and then we have a vacuum system that will siphon out the liquid, and then we add water, allow it to mix, and you do that about 4 times, and then you're ready to set up your next measurement.